All right, good afternoon. My name is Colton Falusi. We are Lab Group 3 for the EEL3110 Circuit Analysis Lab 1. Again, my name is Colton Falusi. My ID number is 6376474.
And
And
my
I'm
name is
Jose.
oh,
Oh, no, you go
sorry.
for it. I knew I was gonna go for it.
all right. My name is Mrs. Briceno. My Panther ID is 608-6235, and that's on Group 7.
All right, and I'm Jose Hernandez, Panther ID 6169293.
All right, and let's see. I guess we'll just go ahead and get started. Looking at activity 1, we have an open circuit, so not too much to talk about here. I don't know. If you guys kind of want to talk about this a little bit, we have some information, but not a ton.
Yeah, so we got one battery and one resistor on this activity. Really, so from VAB, you have 13.5 nanovolts, which is really about 0 volts. We have one resistor, and damn, hold up, we got to start from the top.
That's good.
Hold
You
up.
want to?
Yeah,
Should we restart it?
No, I think it's okay.
Yeah. Oh, we good? All right, continue. Hey, just pick
Yeah,
it up then.
yeah, seems good. Yeah, I think seems good. So we've got approximately 0 volts here. It's showing on, not 0 due to some, things on the simulation. But we know, of course, since there's no current going through this branch, that we're going to have 0 volts across that resistor. VBC, that's going to be from here to here. VDE, from here to here. Those are also 0 volts. What do you guys think? Does that make sense? 0 volts for those?
Yeah, we have open circuits as well, and then for the ADs, the only one's gonna have the 5 volts because pretty much just before.
Right, exactly, because you got AD here. I agree completely, because you got AD going across the positive to the negative terminal of the battery, 5 volts there. And like you said, VDE, it's just right here along the wire. There's no elements between those reference points. Same with VBC.
No circulation.
Yep, no circulation, nothing going on. I1, again, the simulation showing approximately 0. We know that's going to be 0 because open circuit. So not too much math to show there. Again, yeah, open circuit, no elements between those pieces. Activity 2, very similar. We have an open circuit, however, we have a closed loop with one resistor going there on the left side. So I don't know, we got VAB, that's going to be the voltage across that resistor there. I mean, that kind of reminds me of activity 1. In the
With
fact that
3300, yeah.
right, you have in the fact that there's no current going through, so you're gonna have no voltage drop. What do you guys think about the other zeros, the CD and the DEs? Where me?
You got
Yeah, this one
no
right
elements between CD. Yeah, there's no elements.
here.
That'll change
Absolutely.
it, so yeah, it'll be 0.
So that's this one here, and then where the other one? Yeah, that was CD. Where's oh yeah, DE is over here. That's right. Also no elements, exactly like you said. Couldn't agree more. VAD, that's going to be this one across the resistor. So now we're going into the closed loop. What do we think about that one?
Yeah, I think the only reason why we have that is because you have 5 volts flowing through that, pretty much going through the resistor, and then recirculating again, pretty much currents, steady flow. But there is no actual current other than in second current, but the first current we do have. Nice.
Sorry. No, yeah, that makes sense to me. I agree 100%. Like you said, we got that closed loop. So any current that you have coming out of that battery has to go through that resistor and then back into the battery. And all the voltage drop that you gain from that, or sorry, the voltage gain from that battery has to equal that voltage loss across the resistor.
How we can always say, like, looking at these circuits, if you go back to the 6th slide, just looking at it, you can really much tell right away, which are going to have, no flow. And yes, like we do have a flow pretty much. So
exactly. Like I kind of like how they do activity 1 first and then lead it into this one, because activity 2, you can see how the right part of it is just kind of activity 1 all over again. There's
pretty much you get to compare, with you have closed circuit and you pretty much, the first one you don't, but you pretty much get to see, the main difference between the two. That's what I'm trying to say.
Absolutely. Yep. So then the reason we get that 1.5 milliamps there, we can do our Ohm's law, 5 volts divided by 3,300 ohms. Boom shakalaka. And the math agrees. So not too much to talk about there. Activity 4, we got 2 resistors in series. Going through this pretty quick because it's not, not a ton to talk about. You have 50,000 volts here, or sorry, 50,000 ohms here, 5 ohms here to kind of represent one resistance being much larger than the other. Part B, we flip flop those, and part C, we make them equal. So the big differences you're going to see, first off, you're going to see that the current remains the same when you have the same total resistance. So that's why I kept part A and part B. I just flip flopped them and kept them the same total 55 or 50,005 ohms, so that you could see
Yeah.
that that's gonna always be that same I1, I2 is always gonna be the same I. What I should have done is just split it, made it like, take that total, divide it by 2 for part C, but I just made it 5 and 5 to make it easy, because then you could see the current would be the same again. But in this case, you see that the voltage drop ends up the same. That's the main thing we're trying to illustrate here, is that with 2 resistors in series, you have a voltage drop across one is gonna be proportional. It's gonna be a larger voltage drop in terms of it being a larger resistance. So that's what we see in the simulation, and that is what we see in the math as well. I'm not going to take all the time to go through that. I think I went a little above and beyond here. So Anthony, if you want to screenshot that and look at that, you can have fun with that. But
You could explain a little bit, because like you could say, for VCB, the voltage, barely drops, but we do have some droppage.
it's a good point. Yeah, because you can see also, it is a good point. I like that the thing how they have us calculate this V over I, it's basically them having us calculate the total resistance backwards, like doing that Ohm's law and saying like, oh, based on the voltage drop you observe and based on the current you observe, does the resistance check out for that same equivalent total resistance? Oh yeah, we get 10 here. And when you do it here, you get that, 50,005 for the total of the 50,000 ohm resistor and the 5. So it was kind of cool to see that math check out in terms of how it, relates to the simulation. Glad we didn't have to buy the physical stuff though, because I think this is good enough. Seeing that the math and the simulation checks out, I think we're gaining all the knowledge we need to from that.
Props to the professor.
Absolutely, yeah, we appreciate it. Activity 6, similar to activity 4, except the difference here, we've got two resistors in parallel.
Yeah.
So we're gonna have a little bit of a different situation. What do you guys think because of the current? What do you guys think about the current in this one?
You pretty much have to relate. For the 3 different conditions, a couple things do change, but I'm gonna say we still have pretty much a very circulating circuit here still. But I want to say pretty much, if I'm looking at this closely, it goes in a counterclockwise direction. AB. Oh no, clockwise, right? Yeah.
Right. Yeah.
So-
If you're looking from the top, yeah, I see what you're saying. Yeah. But so yeah, absolutely. It kind of makes sense in that way that, when you're looking at the 2 in series, there's nowhere else for the current to go, right? Any current that you're going to have at this point is going to be the same current here, the same electrons, they can't go anywhere. So as opposed to here, we got current that's going to be split up. So we're going to have to see that a little bit in the math. And that, you do see in the simulation first. Well, let's see, you have the larger resistance here. So of course you're going to have a smaller amount of current going through that branch with a higher resistance. So, right, the current wants to go through.
So it just have to get split,
Right. Yeah. It doesn't want to go through the area with high resistance, right? It's like currents are like us. We're lazy. We want to go through the least resistance. So you see least resistance here, you're going to see more current going through that branch.
Just consider like a traffic,
Mm-hmm. Yeah, exactly. And then, similar, I guess you could kind of, contrast it to the other situation where it's like the voltage drop across these resistors, even though these resistors are different resistances, the voltage drops are going to be the same because, it's the same, it's the same node. You have this point here is the same node as this point. It's, whatever potential here, you're dropping a certain amount of potential from this node to this node. This is, you call this, and if we had a highlighter, we could call this, voltage area A. All of this would be voltage area B. And any point here to any point there is always going to be a difference of 5. It doesn't matter how many resistors you have in parallel. The current is going to split similarly to how, the voltage splits here, the current stays the same. It's kind of backwards, right? You got the voltage staying same here, current splitting. So I think we've illustrated the points we want to illustrate here. What? Sorry.
if you compare A and B, I mean, you're flipping the resistance, and then pretty much yeah, okay, the current stays the same. I mean,
Right,
other
the
than
total
flipping, it
current
stays
stays the same, absolutely, yeah, and then you've got
Yeah.
that amount of, oh, sorry, I flipped it to C there, like you were saying there, yep, you got the amount of current kind of splitting depending on that resistance. Exactly like you say, perfect, perfect, perfect. Activity part C, that's the one where you've got the same, so you're gonna
resistor,
see
yeah.
those currents get split equally. And the only real difference in the math here, we have to find those currents by doing that current split equation. So you'll see that here, those proportions taking place. I prefer
Yeah,
to do
100
it this way.
milliamps, correct?
Yeah, 100 milliamps, and I guess, is that the way it shows here? Oh yeah, 100 milliamp.
Or
No.
microamps, yeah.
Yeah, microamps.
Correct?
Yeah, that was micro. Yeah, I read my M's, my U's all the way. I need to get back on that. Let's take a look here. Just make sure we've covered everything on the rubric before we sign off. I think we've covered everything we want to cover. I mean, we've discussed if our systems are doing what they're supposed to do. I think we've covered all that. I mean, if the objectives are met. Any difficulties, guys, that we
I mean,
came
if you
across?
look at A, if you can go back, I mean, maybe even part B and C for activity 6.
Mm-hmm, mm-hmm.
In part C, yeah, you have the same current going through.
Right, you got that split there, so it's equal resistance, because you're gonna have equal current split, so it's gonna be
I
perfect.
just like wonder also like how would this really affect in a real life situation? Maybe like having two resistors the same rather than one resistor being a little, higher in
Right,
ohms.
it's funny because it's like, it's almost like, I can kind of think of it as like, I don't know, like, if you look at, like, I like to look at activity A, because like, think about this large resistor being like the voltmeter itself, right? Like you've got its terminals kind of connecting here. You get no current going through this branch. So that's kind of what a voltmeter is, right? You've got like something with very high resistance connecting to the circuit. Like think of the circuit was just this second resistor, and you had to have something with really high resistance to kind of check that voltage between those terminals, but you don't want any current going through the second branch. That's kind of what we have here if we have like a much higher resistance on that branch than the other one.
Yeah, that's a really good
Kind of
point.
interesting.
That's a really good point.
Very interesting. I think that's enough. I think we've gone over, I don't know how long this recording is, but I think we're good to go. Anthony, thank you very much. Professor Vlasov, thank you very much. Dr. Vlasov, this is Lab Group 3 signing off. If I can find the stop recording button, here it is. Bop.